Hi, it's Matt, and in this video we're going to talk about the first postulate of quantum mechanics. So before we could look at what the postulate actually says, there's kind of some groundwork we have to lay. The first off being with coordinates, which we're going to use Q and T for. So Q is the generic symbol we use as a shorthand to represent all spatial coordinates. So when we say Q, we're not necessarily talking about just one coordinate, but instead a collection of coordinates. And these coordinates give the spatial position, so essentially where our particle or particles is located. So let's look at some examples. So in the case of for one particle, it moving in one dimension, so this would be a particle moving along a line, Q would just represent x, for example, if we were looking at the particle moving along the x-axis. We could also have in one dimension, Q could represent phi with a particle on a ring. So in this case, we would have a graph like this, where it would be confined to move around this circle I just drew, and that dot would be the particle. Here, there's only one dimension, and we would call that angle phi, and that's how we would notate it. So phi, since it's representing the position, is our spatial coordinate and is represented by Q. In three dimensions, Q would represent x, y, and z if we're looking at a particle on a cube. And of course, this is comparable to, in general, when we look at 3D graphs, where we have our x, y, and z axis. So now, we don't need to confine ourselves to one particle. We could have multiple particles, and in that case, Q would represent the spatial coordinates of all particles. So for two particles in two dimensions, that each particle has two dimensions, there would be a total of four spatial coordinates, x1, y1, x2, and y2. And this would be the case for particles on a plane. But the above is not an exhaustive list. Of course, we could have an infinite number of particles, so we would always have the case for more than one particle, where we would have a lot of options. But even for a singular particle, we could choose what coordinate system we want to represent it in. So there are many more than I've listed on this slide, and we'll see some of those later. And lastly, T is the symbol used to represent the time coordinates. So the next piece of groundwork we have to lay is this thing d tau. What is it? So d tau is the differential we use to represent the differential of all spatial coordinates. So for example, if there is a system with one particle moving in a plane, so again that's being able to move in the x and y direction, our spatial coordinates q would again be x and y as we saw on the last slide. So d tau would be the differential of each of these spatial coordinates multiplied, so it would be dx times dy. And in this case, d tau would be a very small square of size, length dx, and width dy. So now as another example, if there is a system with one particle moving on a line, then q would be x as we said on the previous slide. So, since d tau is the differential of all spatial coordinates, we would take that x and put a d in front of it and get d tau equals dx. And here, d tau in this case is a small line segment. So to draw that, if we have our line and this is our x-axis, d tau would represent this tiny little increment here, for example. Now, as another piece, we need to talk about the meaning of this thing called all space. So all space is the term used to denote every possible position where a particle can be located. So as its name implied, all space is just the entire area where a particle could reside. So now let's look at some examples. If we look for a particle confined to a two-dimensional plane, all space would be all possible locations in that plane. So if we define the plane to be the xy plane, then all space would be xy is this set here, so x is negative infinity to infinity, y is negative infinity to infinity. And again, this notation looks a little fancy, but really what it's just saying is if we look at our standard coordinate plane, so we have x and y, all space would just be anywhere in the plane. And again, hence why we could go from y negative infinity to infinity and x negative infinity to infinity. As another example, if we go back to a particle confined in a one-dimensional ring, so remember that was this case we had earlier where we had a particle moving around in a circle, all space would be all possible locations on this ring. And again, if we're marking where the particle is using phi, then all space would be all possible values of phi. Since a circle is 2 pi radians, phi would be confined to be between 0 and 2 pi, so that would be how we represent all space. So now we could finally get to the wave function, psi of q and t. So we have this thing, psi, we'll get to what that is, and it's a function of both our spatial coordinates and the time. So the wave function psi is in general a function, and it doesn't even need to be real. It could also be complex valued of position and time, and it contains all the information about a quantum mechanical system. This is our first postulate, but there's a lot of words here, so let's go through what each of them means. So first off, when we say real or complex, this means that in general the wave function is complex valued, meaning we have both a real part, which I'm calling psi r, and then an imaginary part I'm writing as psi I. And notice we have our imaginary unit I here, where I is the square root of -1. So now let's look at another piece of this definition. And we also see that's a function of position and time. And what that means is, in general, the wave function is dependent on where all the particles are located. So again, where everything is located is given by our spatial coordinates q. But it also, the wave function is determined by what time the system is measured at, hence t, and why our wave function is a function of both q and t. And now, what does it mean when we say contains all information about the system? For that, what this means is that given the wave function, it is possible to find out all parameters of the system, such as position, momentum, angular momentum, energy, etc. Pretty much, if we could measure it classically, there will be some way that the wave function will give us a value for it. So just as we could measure momentum in classical mechanics, that means that there's a way from the wave function we could get the momentum of the particle. And we'll talk about how to do that later. So now let's talk about the probability, which we see as the norm square of the wave function. And we'll talk about what that means momentarily. But first, we need to say that the wave function psi on its own has no measurable meaning. That's not to say it's not significant, though, because what does matter is the norm square, as the norm square of the wave function is our probability density. And this is the probability that a particle will be at a specific position q and time t. So again, this gives the probability of being at a particular point. Meanwhile, we also have, and probably more importantly, the psi squared d tau. And this is the probability of finding the system in a region of size d tau around the specific position q at a time t. So just to draw out what I mean by that, is if we have a particle moving on a line, the probability of it being exactly here is given by this bullet point here. But if we want the probability of it being in a small line segment contained within these red parentheses, then we'd want the probability with the d tau, because again, that's the probability of finding it within a small region. So now, going forward, we want to note that this is not just squaring the wave function, but instead taking the norm square or the absolute square. You also may hear it as the modulus square, depending on what book you are reading. And what this means is to multiply a number by its complex conjugate. So again, it's not just squaring, it's multiplying a number by its complex conjugate. And what's so special about the norm square is that it will always give a positive real number. And that's important because we said up top that this is a probability. We know that probabilities are going to be positive, and they have to be real, because a negative or an imaginary probability wouldn't make sense. And so, just as a quick exercise, I'm not going to go through the math on how we do this, but you should on your own for practice. So given a generic wave function that earlier we said has a real and an imaginary part, when we take this norm square, we find that we get the real part squared plus the imaginary part squared. And again, since both of these are real numbers squared, we know that this will always equal something that's real and also greater than 0. Or I guess I should say greater than or equal to 0. So now that we've talked about what the wave function is, let's talk about the requirements for it. And the first one is that the wave function must be single valued. And what this means is that to be acceptable in quantum mechanics, that for any particular set of position coordinates q and time coordinates t, the wave function can only have one value. And this makes sense because if it has multiple values, that means when we take the norm square, there's multiple probabilities. And if we're at the same point and the same time, there should only be one probability. Anything else wouldn't make sense. So as an example, let's look at this graph here. On the y-axis, we have our wave function, so psi of, I'll call it x and t. And then we have x on the x-axis. So we see that this is an acceptable wave function because for any x value, we only get one singular output value. So this one's good. However, if we look at the same scenario over here, but a different graph, this one is not an acceptable wave function. And the reason for that is, if we take the point -2, for example, we find that up here and down here both correspond to that point. Meaning that for the same x coordinate and what we're going to say the same time, there are two different values for the wave function, and that's not acceptable, meaning this is not a valid wave function. Another requirement we have is that it has to do with continuity and differentiability. For the wave function to be acceptable in quantum mechanics, it must always be continuous. And here, continuous has the same meaning it does in math, where the limit from the left equals the limit from the right equals the value of the function. But we could think about it in the simpler sense of, can I draw it without lifting my pencil? And also, as another requirement, usually the wave function also needs to be differentiable everywhere as well. This requirement, there are some cases where it's not true, but it's definitely important to always keep this one in mind. So now let's look at an example. So we have two examples on the graph here. Again, we have psi of, I'm just going to say q and ignore the time dependence for now. And then we have q on the x-axis. Here, q is just x. So the blue function is good because if I trace it over, we see that I'm not lifting my pencil. It's all good. It's continuous. It's smooth. So it's differentiable as well. However, if we look at the yellow and we start tracing it, once I get to 0, I need to jump up here, meaning it's discontinuous at x equals 0, so the yellow function is not acceptable. And now, as a final requirement, we have that the wave function has to be square integrable. And let's talk about what this means. So for a function to be square integrable, this means when we integrate across all space of the norm square of the wave function, we need to get a finite value. And this would imply that the wave function must be finite at all points as well, since if the wave function goes to infinity anywhere, that would imply an infinite probability of being found at that point, and again, that doesn't quite make sense. But it would also imply that as we approach the bounds of motion, when I say the bounds of motion, that's just really a fancy term for plus or minus infinity, or as far out as the particle could possibly go, the wave function must go to 0. Because if it levels off to a non-zero value, when we integrate, we're going to get infinity, which we said was not okay. So again, since the norm square of the wave function is the probability of finding a system in a region of size d tau around the specific position q at a time t, the integral across all space of the norm square of the wave function must be 1, since the particle has to exist somewhere. I know that might be a little confusing and a lot of words, but what this essentially means is that the particle has to exist somewhere. So if we look in the entirety of the universe or the entirety of all space, the probability needs to be 1 or 100% because the particle exists. And the particle has to be somewhere. So if we were to find that the integration across all space of the norm square is not 1 but is finite, we could then normalize the wave function so that it does equal 1 and make it good that when we integrate across all space, we find an 100% chance to find the particle. But when we integrate across all space and get infinity, normalization is not possible, which is what makes the wave function invalid. That inability to normalize and make it that the probability of finding it anywhere is 1 or 100%. So now, just continuing this, let's look at an example. If we look at this function here, it's not normalized, but it can be normalized because we see it goes to 0 as we go towards the bounds of motion. And it's bounded by above, meaning because it never goes above 1. This means when we take the integral or find the area under, that means we're going to get a finite number, meaning it is square integrable, and we would be able to normalize the wave function. So this one is okay. However, to the contrary to that, on the right, we see that it doesn't level off to 0. Instead, it levels off to 1 as we go towards positive and negative infinity. So when we take the integral and find the area under our wave function, as we go towards plus and minus infinity, we're going to get that the integral equals infinity, meaning this is not square integrable, so this would not be a valid wave function. Thank you so much for watching. I hope this helped. Feel free to leave any questions or comments you have in the comments below. Thank you so much and have a good day.